Okay, good morning, students. So in this lecture, I'm going to explain about the turbulent flow, okay? Mainly the transition and turbulent flow. So in my last video, I talked about the lift and drag. So I hope you already have some idea when to, why we need the lift and drag coefficients that I already explained. So if you know the coefficients, so you can use it for different design purpose. And you also know that how we can calculate the lift and drag from the normal pressure force and the shear force, right? It means you need to consider the component of the normal pressure along x direction and y direction, and a same way you also need to consider the component of the shear force or shear stress, whatever you like, you can say, along the x direction and y direction. And you also know that the lift force always acts perpendicular to the flow direction, and the drag always acts parallel and along the flow direction. Okay, so you already have those ideas. So from now on, I'm going to explain about the turbulent and transition flow. Okay, so you already know that how to calculate the boundary layer thickness, the displacement thickness, the momentum thickness. Okay, we will solve some problem. Okay, later on, then it will clear the idea. Okay, how to calculate the things. Okay, so before going to that, I'm going to finish the lecture part. I mean the theoretical part for this week. Okay. So turbulent, you already know that when we have the flow over a flat plate, first we have the laminar flow. Then with the increase of the x, the flow becomes gradually transition, and then it turns to turbulent flow. Okay, so when we have the turbulent flow, mainly we experience the AD, and we will have the velocity gradient. Um, okay, so this one I cannot write. Hold on, I need to restart. I'm sorry for that. Okay. No, okay. So what I'm talking about, the turbulent flow, it means the structure of the turbulent boundary layer is very complex, okay, and we cannot define it in any particular equations. Is random and is of course is irregular and nonlinear, and the velocity is also unsteady. It means like it will change with the time. Okay, so this is just an experience from the wind tunnel. If you have the cylinder or any spherical shape, so beyond it, as you know that at this point the separation will occur, right? So I already explained the things in my last video. So how the pressure changes and how the velocity changes. So at this point you will have zero velocity. It means the flow will separate from the body, and after that the velocity there will be negative pressure, right? So due to that negative pressure, and there is a hollow line, I mean there will be some this space where we will have a vortex. Okay, so we will have the AD, so it will like circulate the motion at this point. So this AD becomes very it could extend up to some length, and for this region we have we have the turbulence zone. Okay, and in this case the velocity is totally nonlinear, is irregular, and also it's completely unsteady. It will completely change the velocity will change with respect to time. We cannot define the things with some equation. Okay, anyway, so next is the how the velocity changes. Okay, the velocity profile normally, as I said, is non-linear. Okay, so normally if we consider the turbulent flow of incompressible fluid, we consider the velocity profile is like this. Okay, if you remember in the first or second video, we had this kind of plot. We have u by u infinity. I think we will have, I'm just drawing it opposite way. Anyway, so you can draw in either way, it should be okay. So if you have u by u infinity, and if you have the y by delta, um, low noise makes problem. One moment. Sorry. Okay, now I can write, I think. Okay, so if you have y by delta, so if you want to draw the plot in non-dimensional form, that is 1 and 1, in case of turbulent model, so in turbulent flow, this profile is like this, okay? And in case of linear, is actually most of the time is either is like proportional, or most of the time is actually parabolic, okay? My drawing is not accurate. Mainly this one is for laminar flow, that is parabolic, and on the other hand, for the turbulent flow we consider is like 1/7 power. So 1/7 power method, we call it something like that. It means that we consider the relationship is u by u infinity is equal to y by delta to the power 1/7. So we always consider this one when we consider the turbulent flow. Okay, so if you have this relationship, so based on that, so we can actually derive the boundary layer thickness, displacement thickness, right? Momentum thickness. We can also derive the wall shear, frictional drag. All the things can be determined. Okay, so we will solve the problems, okay, later on. So how we are going to find out this, you already know how to get the displacement thickness, momentum thickness, so we will learn more about the wall shear and then frictional drag in the class. So most of the time, so in case of shear stress, for the pipe, you remember is a pipe. So far we have investigated the flow over a flat plate, but this one in case of pipe we consider is rho u square f by 2. F is a function of eta. You already know that, and you also know that u by u infinity is equal to f. Anyway, so this is the relationship, and if r is the radius, so wall shear stress is defined as half rho u bar is the average velocity, in this case mu by u bar u to r to the power 1/4. Okay, so this one no need to derive. This one just remember that if you have the radius of the r of a pipe, so we can consider the wall stress like this. And if r is considered or assume as a boundary layer thickness, okay, we just consider the r is the boundary layer thickness is like equal to the r, then this tau, that is wall shear, can be written as constant multiplied by rho u square mu by u delta to the power 1/4. Okay, remember that this one is wall shear, that is the shear stress at y is equal to 0. But we also have the wall shear yw, where that will change with the y. Okay, so that is not at y equal to 0. So I will disclose this equation later on. So far remember that tau naught and tau w is not same. Okay, tau naught is the wall shear, that is y is equal to 0. Let's consider this one is a constant, and then rho u square, this is the expression. If you remember from the Volckermann integral, this one was how about that one? If you remember, that is rho u square, you had del theta by del x, right? And theta is also a function of x, so if you differentiate you will get these kinds of thing. Anyway, so for the pipe in this case, if just it's a constant, and then this is rho u square is coming from here, and then we have that del theta by del x. In this case you have mu u theta, sorry, delta, and then to the power 1/4. Okay, and if you remember this one, so according to the Volckermann equation, if this is the tau naught, according to the tau naught also you know that rho u square, this one is alpha, if you remember. That is alpha, and then we have d delta by dx. If you remember this one, we already had this equation. Okay, so we have different form. Okay, for according to the von Karman equation, we have different forms. So if you want to have a look, let's try to open it. Okay, so if I go down, so we have this one. You can see tau naught is equal to rho u square alpha and d theta by dx. And alpha is what? The integration. In this case, the alpha is here is this. Alpha is 0 to 1, u by u naught, 1 minus u by u naught eta. It means actually we are replacing the y with eta. Okay. So if you remember from my explanation, so alpha is like this. You have to remember this one. And so we have this expression here. So rho u square alpha and theta dx. Okay, so we have different types of form. Okay, so if you go and then you can imagine that when we have the alpha value already calculated, so 2 by 15, right? So then we have different expressions for each of these. Okay. Okay, so these things are just to show that how we can get these things, this equation, right? So this is alpha. And then the Prandtl equation. So Prandtl do some. This is a scientist also. He did some experiment and he found that this constant value. Okay, so this constant value is 0.20229. So if you put this constant value 0.0229, so and then you reshuffle, this is equal to this one, and this one is actually alpha. So what you will have? You will have this one delta to the power 4. Okay, so this delta to the power 4, this will go to the left right hand side, so it will go here. That's why we have this. And then this is a constant, so this constant is here, and this rho u square that will be crossed down, and then we have the alpha here, right? So this alpha will go here, and we have this extra term that is we have this mu and delta. delta is already there, I'm sorry. So we have the small u and capital U. Okay, so then we balance it. Okay, so after that normally you will get this one. You can try to derive this one. Okay, so just simplify it by shuffling the variables to the left hand side and right hand side. You should get this. And in this case you will have the alpha, as you know already. This is the value of alpha. Now what you need to do, this alpha you need to find out for your turbulent flow. Okay, so you know that u by u infinity in this case y by delta to the power 1 by 7. So y by delta in this case is actually eta. So alpha should be what you will get. You will get the value, this is u by u naught, right? So this is eta to the power, just put the values, eta to the power 1 by 7, 1 minus eta to the power 1 by 7. You integrate this one, put the values, and then if you simplify, you will get this. Okay, do it by yourself. Just integrate and put the value u by u infinity is eta to the power 1 by 7 multiplied by 1 minus eta to the power 1 by 7, and then simplify it 0 to 1, you will get this value. So if you get this value, what we can get, so just put the value here. It means just put the value of alpha in this case here. Okay, I think this one is wrong. Okay, so please forgive me. Okay, sometimes this expression is wrong here. This should be, if I'm not mistaken, is becomes I don't know why so many mistakes. U by new. So u by new. Okay, if I say like you will get this one and you are not getting the values, okay, please let me know. Please let me know, because there are so many type mistake. Okay, because honestly it's not made by me, so I just follow it to deliver the lectures. So sometimes I am not deriving the things. So if I derive, I will know that this is okay, this is not okay. So I just ask the students, ask you, derive and reconfirm. Okay, don't believe everything is correct here, so just derive and make sure like the derivative that you, the value or the expression that you get is matching with this. If it is not matching, either you are wrong or here is wrong. So how I know that this one is wrong? So you can see this is the correct expression. Okay, so this is the correct expression, so just putting the value of alpha, you will get this one. So now, if you have this delta, then you can this expression. From this expression you can get the value of delta. How you can get the value of delta? Just you shuffle it. 1 by this one delta d delta is equal to all the things that you have. Then you have dx, right? Then you integrate and then integrate. So if you integrate, this is all constant value. You will get only x in this case. On the other hand, for this one, you will integrate and you will get some values. Okay, it means delta to the power this plus 1 divided by something. Okay, so it should be 1 plus 5 by 4, right? So here you will get 5 by 4. Please do it, okay, by yourself, and then if you shuffle it, so 4 will be somehow cancelled out. Okay, at last you will get this expression. Please derive it. If I say that if the value is like this, for the turbulent model, if this one is given, then I might ask you to just I will give you the hints. I will not ask you to derive from the beginning. Might be you need to do the simplification, and then you just put the values, you will get this delta. I mean, this is the boundary layer thickness. Okay, is a function of x. So this expression is for turbulent layer, because for a turbulent flow, because we in this case we consider u by infinity is equal to y by delta to the power 1 over 7. Okay, then if you know the delta, and actually if you know the u by u infinity, so you can calculate this one, and this one also is possible to calculate. Okay, so that's the same way that you calculated this delta for other flows. So same, just you need to substitute this one with y over 7, y over delta to the power 1 by 7. That's all. Okay, so please try to do it. I hope you will get the answers. Okay. um, okay, this is clear. I hope you understand. So just in the expression of displacement thickness, just you need to substitute this one, y by delta, and then delta is actually the function of here, right? So you need to also put the value here, delta value. Um, or if you just put in the form of eta, in this case, or just put the value of y by delta to the power 1 by 7, that should be okay. Let me cross check what they did. Okay, theta. Okay, anyway, for now being, just you derive this one and you just believe that if you just put the value of this and simplify it, and you've also, of course, you need to put the value of delta here, then you will get the expression in this way. Okay, we will solve some problem, then you will know, get used to know about the things in more better way. Then we have this stress, I mean the wall stress. Okay, so if you remember, the wall stress expression was This is your wall stress expression, right? So if you remember, this is wall stress expression. So the tau naught will be in this case 0.0229. Then we have rho u square, and then we have this part is you have the delta. So delta, you need to put the value of delta here. So what you will get, so tau naught will be in this case 0.0229, then multiplied by rho u square, and then we have this to the power 4, right? This is mu u delta to the power 4, 1 by 4. So this one you need to also put the value of delta. So in this case, the delta, the value of delta in this case is, where I can write so I'm sorry. So value of delta is this one, 0.376x divided by rs to the power 1 by 5. Okay, so if you substitute this value here, okay, what you will get, I'm sorry, I have some calls too, so I'm distracted. I'm sorry for that. So if you put the value here, delta, so delta was what I said, delta is actually 0.376x, then rex to the power 1 by 5. Okay, so if you put this one here, what you will get, so you will get like 1 over 0.3769, okay, to the power 4, and then we have some other expressions. You have to simplify it, okay, and you have to simplify it. If you simplify it, this is also your task, you will get this one. Definitely you will get this one. Remember that I'm not going asking you to derive these things, but you will get how to get these things. You need to know. If I substitute the value of delta is here, okay, so this is the delta part, and then if you simplify it, you will get this expression. And the drag force, how to get the drag force in this case, the frictional drag in this case is actually, you know that we will solve some problem tau naught if you integrate the b and x is actually it means that if you multiply the stress by area, you will get the force, that is the drag force, okay. So in this case, the tau I am multiplying by the area, so in this you need to integrate, so dx, and you have the b is the breadth. Sometimes the b is unit width, so b is actually 1. So if your b is 1, you just need to integrate the tau with respect to x. So if you just need integrate this tau with respect to x, in this case you need to integrate 0 to L throughout the whole length. Okay, so that's why we have the L here. Just if you have the x, you need to replace it by L, okay, and then you can have this expression also. Average friction, this one is also I think something is wrong here. Anyway, we will see the equations later on when we'll try to solve the problems. Okay, so in short, it means that every time whenever you consider the Von-Karman integral, or you can consider the Blasius form, or in case of turbulent flow, Von-Karman integral and the Blasius form, these are for laminar flow, okay. But in case of turbulent flow, all three cases, you need to know that we can derive the boundary layer thickness, displacement thickness, momentum thickness. Then also we can derive the shear stress, wall shear stress, the frictional drag, and the frictional drag coefficients. Okay, these are the all expressions you can calculate. This is a summary. Transition flow, this is already all about the turbulent flow. Then we have the transition flow, that is very simple. That is the transition flow is the mixture of laminar and turbulent. Okay, this is the transition from laminar to turbulent flow. So we will have them both characteristic here. Okay, so normally if you consider the flow through a pipe, so we will have the turbulent at the center and the laminar flow should be nearby the edge. Okay, And remember that each of these flow behave in different manners in terms of frictional energy loss while flowing, and have different equation predicted that predicted their behavior. So also for transition flow we have different equations that can predict the behavior, means momentum thickness, displacement thickness, they have different expressions. And the parameter, actually turbulence, whatever it is, it depends on the Reynolds number, you already know. Reynolds number means depends on the value of x. Okay, so Reynolds number depends on the roughness, that is mu, viscosity, the curvature of the surface, that is actually also the viscosity, and the disturbance flow outside the boundary layer. So these all are actually based on the mu, reflecting the mu here. Mu or nu, whatever you like, you can say. And if your plate has a sharp leading edge, so you will have the transition take place at a distance x from the leading edge given by like this. Okay. So if your Reynolds number is like this, we can find out the value of x. Okay. So at which, so for this Reynolds number you can get at what position you will have the transition. Okay, so these are actually the theoretical part, and what is said here is a problem. One a simple problem is given for you. A fluid flows steadily past a flat plate with a velocity of u. It means the free stream velocity is this much. Find at approximately what location will the boundary layer become turbulent. It means you have to find out what is the value of x at which the laminar flow turns to turbulent flow, and how thick is the boundary layer at the point of, that is when the water temperature is 15 degree. What is the thickness of this? It means you also need to find out the boundary layer thickness. Okay, so how we are going to find it out? The solution is already there, but you need to think. So first of all, as you know that the transition depends on the Reynolds number. Okay, of course it depends on the Reynolds number, and it said that the value of x, if you want to find out the value of x when it turns from the laminar to turbulent, you need to consider the laminar flow, sorry, you need to consider the Reynolds number in between 2 to the power 2 into 10 to the power 5 to 3 into 10 to the power 5. So you can consider either of it, okay, in between of it. So in this case, you need to find out the Reynolds number. So you already know that Reynolds number. So Re, in this case, if you want to find out x critical value we use it because it defines a transition point. So x critical Cr is actually u, and then we have the x. You can consider xCr, okay, divided by mu. Okay, so it means we have rho by mu, that is nu. So this one is equal to 2 to the power 10 to the power 5. So you already know this one. You already know already know the viscosity in this case. If you don't know, just put the value like mu in this, as shows in the example. I don't know this one because that's why I just put the value is like this, and you already know. So x critical is as a function of viscosity. So depends on the viscosity, you will have that you can determine the position x at which your laminar flow turns to turbulent flow. Okay, next, this is the answer already, and the next one is the boundary layer thickness. If you remember that in case of gaseous form, we found that when the eta is 5, your u by u infinity becomes 99%, right? Or 0.99. So from that equation, gaseous form, so we know that the delta critical is 5 root over of mu x critical by u. So before we had that delta critical is actually 5 maybe x root over rex. Okay, anyway, I'm not sure about this one, but the equation is actually like this. You can represent in the rex form, should be okay also if you want to like that. If you want to like or you want to put in that form, because you have the x critical, so we want to substitute the value of x. So you have this value of x, you just put it here, and then you will simplify it, then you will get this expression. Okay, so all you need to know, because the x critical and the boundary layer thickness depends on the viscosity. Okay, so at 15 degree you can check in the internet. So for the fluid, I mean the water, at 15 degree the viscosity is this much. I don't know, it's water or flow caster plate, find the location, wonder how they go. Fluid, which fluid is didn't mention, I don't know, maybe it's I think it's a, in this case they consider it as a water or any fluid. Anyway, the value should be given to you, don't worry. So whatever value you just put the values, you will get the expression for x critical and delta critical values. Okay, that's straightforward. Okay, so that's all for this theoretical part. So in my class tomorrow, I will try to solve some problems. Okay, that will give you more confidence to solve any types of problem. Okay, thank you very much.